your assignment before this was to read the section in the book. If you didn't, this is going to be very new. And anyway, number one, or at least the example, you have air blown into a spherical balloon at a rate of 3 cubic centimeters per second. It's important to note that this rate is a volume per unit time. So you're inflating this balloon by a set volume per unit time. And it wants to know that as you inflate that, how fast is the radius of the balloon increasing, specifically when the radius is 4 centimeters. So what's important to note is that when you fill this balloon up, its radius is not going to increase at a constant pace. It's going to change. As the balloon gets bigger, the radius increase is going to slow down. So the first equation, the equation of the first graph, this is a graph of volume for time. And it says air is blown at the rate of 3 cubic centimeters per second. So as I look at this and I see the slope of up 3 over 1 and a y-intercept of 0, 0, the equation of this first graph is going to be volume is equal to 3 times time. Actually, y is equal to 3x, but it's not y and x, it's volume and time. The slope is 3, and it's a change in volume over a change in time. Now, if you look at kind of what this is asking, we have this graph of radius per time, and here's the graph of what the radius is doing. And specifically, at this point right here, we want to know what's the instantaneous rate of change. So to get that, we're going to look at this right here and say, all right, so that's the volume. What is the change in volume over the change in time, dv dt? And if I derive the left side, or take the derivative of this, v prime, or dv dt, is just equal to 3. That's the derivative of this one. And that should make sense. That's actually the slope, change in volume over change in time, so that matches. But we are trying to find dr dt, the instantaneous change of the radius for time. Again, the slope of this line right here. Again, dr dt is the same as change in radius over change in time. Are dr dt and dv dt and dr dt related? Well, yes, they are. As one increases, the other decreases, or there's a relationship between them. What's the formula for the volume of the sphere? This you should know: 4/3 pi r cubed. You're going to want to have that memorized. And then dv dt. Well, we want to find dv dt, and we did find it up here. It's equal to 3. We want to find it with relation to this r. So what we're going to do is actually take the derivative of both sides of this with respect to t. So I'm going to say dv dt equals, then I'm going to do the derivative of r here, which is dr dt, and then the derivative of everything is 3 times 4/3, or 4 pi r squared. So I just took the derivative of both sides with respect to time, a new variable. And then when I take that, I can find dr dt by, this should be dv dt, by plugging in 3 for dv dt, dr dt, 4 pi. Radius at the point that we wanted to take was 4, according to the problem, so that's 16. And I get 3 over 64 pi centimeters per second is equal to dr dt. So kind of read this. You'll not need to go through all the above steps to solve these problems. The key equation you'll need is the one that relates these variables. This equation can be found by taking the volume equation and differentiating of each variable with respect to time. In our problem, we had v is equal to 4/3 pi r cubed, and we differentiated all with respect to time using implicit differentiation. So now instead of adding dy dt dx or y prime or anything, we're just going to add these dv dt's or dr dt's or whatever. We take the derivative with respect to time. So pause the video, read these 2 paragraphs, come back. Okay, next example is just kind of some more setup. Suppose we have the area of the square with side length x is increasing at a certain rate. So here's a square. Oops. Square with side length x. I'm going to kind of throw a picture down. Crap. And we have area. So I'm going to put area is equal to x squared, and differentiating the area function with respect to time means dA dt equals 2x dx dt. suppose the volume of a rectangular solid with square base is increasing at a certain rate. If it has a square base, then it's going to look something like this, where we have x, and then our heights are kind of an unknown, so that's a height of h, and volume would be x squared h. And so differentiating the volume with respect to time, well, we can do dv dt equals, and I'm going to do product rule here, first times the derivative of the second, x squared dh dt, plus, then second times the derivative of the first is 2x h dx dt. So here's the steps. Sketch a picture, label it, include variables for unknown quantities, identify any constants, then write down all known facts expressing the given and unknown rates as derivatives, and we'll kind of do that. The rates as derivatives is kind of important. Write any equation that relates to variables, like volume equations and area equations. Differentiate all variables with respect to time. Substitute the known values and rates, find the final answer. Make sure you put appropriate units on the final answer. Okay, this is kind of stuff we're going to do here, so let's just get started. Number 3, spherical balloon inflating helium at a rate of 100 pi feet cubed per minute. How fast is the surface area of the balloon increasing when the radius of the balloon is 5 feet? Okay, well, I have a volume, so I know that volume is 4/3 pi r cubed, and I know that the surface area formula is, you can actually memorize this as the derivative of volume, 4 pi r squared, and it wants to know when the radius is 5 feet, and it says this is 100 feet cubed per minute, so that's dv dt equals 100 pi. Okay, that's pretty much everything we know. So I'm going to derive the first one. dv dt is equal to 4 pi r squared dr dt. Well, I'm able to substitute pretty much everything in and find dr dt. So maybe I can use that in the surface area equation. If I take dsa dt equals 8 pi r dr dt, then I can substitute this once I find it back in here and figure out what the change in surface area is. And that would answer how fast is the surface area increasing. So going back to the first one, dv dt is 100 pi, 4 pi, r squared is 25, and then times dr dt. Well, if you look at what this is just 100 pi, and that's 100 pi, so 1 is equal to dr dt. And we're going to take that and plug it in here. So dsa dt is equal to 8 pi times the radius of 5 times 1, and that's equal to 40 pi. And units of that would be feet squared per minute. Next one, 2 commercial jets at 40,000 feet are flying at 520 miles per hour along a straight line course that cross at right angles. How fast is the distance closing? So pretty much what I have is one plane is doing this, where it's flying like that, and the other one's doing this, where it's flying like this. That's not really right angles, but you get the idea. We'll call that a right angle. Here's A, here's B. They're both flying at 520 miles per hour. 520 miles per hour. The 40,000 feet is irrelevant because we don't really care. We're looking at a snapshot at that point. They're not going below that or above that. They're just kind of chilling at 40,000 feet. And what I have in terms of the 520 is I actually have dA. If I sort of define this little thing as A, this is a distance of A, this is a distance of B, with little case, then this could be dA dt equals 520. dV dt also equals 520. And it says how fast is the distance closing when airplane A is 5 miles from the intersection. So A equals 5, and then B is 12, B equals 12. So I'm going to put A equals 5, B equals 12. Check that the units all match. They're all miles and all hours. and it wants to know what the distance is. So I need to sort of put this, that was a terrible connection line, let's just make it a line. We'll call that D, capital or lowercase, doesn't matter. And I want to know how fast is the distance closing. So not what the distance is, but how fast is it. I know when A equals 5 and B equals 12 that D would have to be equal to the square root of 5 squared plus 12 squared by Pythagorean theorem, which is 13. So I could even say that I know D is equal to 13, and I want to know what dt is. So with all this information, we need an equation that's going to relate to all three of them. Well, I can start with d squared is equal to a squared plus b squared, and then derive that so I can find the rates of change. That'd be 2d dt equals 2a dA dt plus 2b dB dt. Cancel out your 2's and start substituting. We're looking for dd dt, so actually I'm going to write that by itself and with the others sort of with a fraction bar all over d of 13. A was 5 times 520. B is 12 times 520. That's actually equal to 17 times 520 over 13. 13 divided into 520 is 40, so that's 17 times 40, which is 34,680 miles per hour. 13-foot ladder leaning against a house. So if I kind of draw this out, oh, I don't need the arrows. There we go. And we have a 13-foot ladder kind of leaning against the house, so I'll put something like that. That's fine. So 13 feet, its base starts to slide away. By the time the base is 12 feet from the house, so I'll put x, call this x, and I'll say x equals 12. The base is moving away at a rate of 5 feet per second, so dx dt is equal to 5. We know that x is equal to 12. This is constant, so I'm not going to define that as a variable because that one's not changing. The ladder will always be 13 feet. We can call that h, and it wants to know what it is dH dt. How fast is it sliding down the wall? So if we kind of keep that going, I suppose I can do the same thing that we did before. 13 squared is equal to x squared plus h squared. And it wants to know what dH dt is. So we can also kind of plug in, I should know what h is. 13 squared minus 12 squared is 5. So h would be 5 by Pythagorean theorem. So when I derive this, we get 0 is equal to 2x dx dt plus 2h dH dt. I can cut the 2's out again, and I get 0 is equal to 5 times 12 plus 5 times dH dt. And that would mean that dH dt is equal to negative 12. I mean negative 12 feet per second. And it's negative because it's sliding down. That makes sense. Then it wants to know how fast the area of the triangle formed by the ladder wall and ground is changing. Well, area is equal to 1/2 base times height. So dA dt is equal to 1/2 times, and I'm going to do product rule. That'd be x dH dt plus h dx dt, which is equal to 1/2. See, x was 5 times 12, and then h was 12 times 5. Oops, sorry, no, 5 times. I'm messing it up. X was 12, and then dH dt was negative 12, so it's 12 times negative 12. Plus, and then h was 5, and dx dt was 5. So when you add this up, you get negative 119 over 2 feet squared per second. Two trucks leave a depot, one going east and one going north. I can model that by this, which I'll now move up. Okay, this is loving moving. Apologies. Okay, that's fine. No, it's not. Let's move that over. Laugh it up. I am really trying here. Okay, so that's A, and that's B. And it's a distance one, so we can call this little a, we can call this little b. Little a is going 40 miles per hour, so that's dA dt equals 40. Little b is going 30 miles per hour. Oops, don't put equals, because that's not a distance yet. So that's 30 miles per hour. So dB dt is 30. How fast is the distance between the convoys changing 6 minutes later? So 6 minutes after they leave. Well, distance is equal to rate times time. So the distance for A, or I can just say A is equal to A's rate, 40, times 6 minutes. Now 6 minutes is 1/10 hour. So 40 times 1/10, that's equal to 4 miles. So I know that when I take my snapshot, A is equal to 4. Let me switch the A and the B here to keep this consistent. B is equal to 1/10 times 30. Which is equal to 3 miles. 3, 4, 5 makes a Pythagorean triple, so we can call this capital D for distance. It wants to know how fast the distance is changing, so I can launch right into a dt equation. Remember, d squared is equal to a squared plus b squared. Again, by Pythagorean theorem, I can say, well, let's do the deriving. 2d dt equals 2a dA dt plus 2b dB dt. Cross out your 2's. It wants to know dd dt. Let's do the solving just like we did before. We're pretty much almost done. 4 times 40 plus 3 times 30 all over 5. Work that out and you get 50 miles per hour. Lastly, balloon rising. So here's a balloon rising above a level straight road at a constant rate of 1 foot per second. So I think I'm going to call that H, especially as it says the balloon is 65 feet above the ground. And when the balloon is 65 feet above the ground, a bicycle passes under it. I cannot draw a bicycle right now. Bicycle going 17 feet per second. How fast is the distance between the bicycle and the balloon changing 3 seconds later? So that can be a capital D. So I want to know what this X is and what this H is 3 seconds later. So 3 seconds later, X is 17 feet per second times 3. And that would be 51, so X is 51 feet. And then 3 seconds later, H is, well, it was at 65 feet, but it'd be 65 plus 3 times 1 for the 1 feet per second. That'd be 68. 3 seconds later, that balloon is at 68 feet. So another Pythagorean theorem, 1, d dd dt equals H dH dt plus x dx dt. I skipped the Pythagorean theorem and I skipped putting the 2's there because we always cross those out. And dd dt would be equal to 68 times 1 plus 51 times 17 all over 85. Oops, I need to tell you where I got the 85 from. Sorry. Where did I get the 85 from? Well, got it from d squared is equal to h squared plus x squared. If I plug in, let's see, if I plug in the 51 squared plus 68 squared, I would get d is equal to 85. I'll let you solve that and figure that out. So d is 85, divide, and you get 11 feet per second.